So it's a pleasure to chair this session, which is the second session on quantum optics and cavity QED. Our first speaker is Vladan Vuletic from MIT. He'll talk about what does the golden rule have to do with friction, and answer atom by atom.
Thank you very much. It is my great pleasure to be here, and thank you for the invitation. I also apologize because I'm in a cavity QED session, and what I will tell you about is a completely classical system. However, I would like to convince you that even already the classical physics of a few interacting particles, in this case ions connected to lowest order with springs, gives you some surprising and nonlinear and surprising and non-intuitive insights about the nature of friction. This work was performed in collaboration with Alexei Belinsky and Dorian Ganglov, who were leading this experiment. And some of the experiments have been done in very close collaboration with our esteemed organizer, Won Ho Jae, who has been in this business of friction for a while, and who, unlike what we do together, studies real friction in his systems. So what I would like to tell you about is so-called stickslip friction. So it's dry friction. There's a single particle model of friction that goes back to Prandtl and Tomlinson, back to 1928, so almost 90 years old. And then I would like to tell you about how we realize this model in our ion trap system. And as a warm-up, show you some single particle results. And then we come to the much more interesting case of a many-particle model of friction, which is closely related to the so-called Frankel-Kontarova model. And there I would like to show you that there are some quite unintuitive results regarding the arrangement of particles relative to the frictional surface that have very strong effects. In particular, there's something that people have called super lubricity. Maybe it's more appropriately called structural lubricity, and the famous so-called Aubry transition of how chains of interacting particles localize in a periodic potential. The work we do was not invented by us. It goes back to proposals by Szepeljansky and Erio Tosati, and some beautiful papers written by Hartmut Heffner, who these people proposed that interesting physics on friction could be studied in ion traps, and Hartmut made it more concrete, if you want. And it was his work that actually drew our attention to this interesting problem. For me, friction was always quite mysterious. There are these very simple classical friction laws. One is, for instance, that the friction force is proportional to the normal force with which an object presses on the surface. That's maybe not unreasonable. It's some kind of linear law. The harder you press, the more friction force you need. Already the fact that the friction force, the dry friction force, is independent of velocity is quite surprising. We know that, for instance, in air friction, objects moving through air, there's a strong velocity dependence here. However, for dry friction on surfaces, it's independent of velocity. Simple but surprising. And maybe the most surprising of these three laws is that the friction force is independent of surface area. Naively, you might think that friction is some kind of sticking, and therefore the larger the surface area is of an object, say two objects of the same mass but with a different contact area, the larger the area here, the larger the friction force should be. And yet, that is not the case. So I would like to show you measurements that elucidate a little bit what happens at the nanoscale, where we can understand things much better. These laws, by the way, go back all the way to Leonardo da Vinci. He, however, never published them. They were discovered after his death in some of his notebooks. So he studied friction already a few hundred years ago. So I would like to re-examine these empirical laws at the atomic scale. When my students Dorian and Alexei came to me, they had just read Hartmut's paper and said, oh, this is very exciting, we should do it. I was a little bit wary because I remembered that Wolfgang Pauli had said, among other things, God made matter, but surfaces were the work of the devil. So, surface physics is complicated and not always as clean and nice as quantum physics is. And on the other hand, Wolfgang Pauli has also said, das ist ein Schmutzeffekt, mit Schmutzeffekten befasse ich mich nicht. This is a dirt effect, and I don't concern myself with dirt effects. Truth to be told, he didn't say this about surfaces and friction. Does anybody know what the topic was? This was semiconductors. Okay, so maybe one should even take his advice with a little bit of caution as well. So However, one can say that maybe some 10, 20 years ago, because it was very hard to predict anything about macroscopic friction from first principle, most physicists had left this field. This has, however, changed recently, and there's a renewed interest in tribology, especially at the nanoscale. And one of the reasons is that chemists can build, for instance, now really nanoscale machines. They can build machines on the order that have tens or hundreds of atoms. This is, for instance, a car that moves on a surface when you inject electrons to it. They can build little pumps and so on. And on the nanoscale, nanomachines are really severely limited by friction and frictional tear and wear because they are so small. Well, the simple argument is frictional scales as area, and the atom number in an object scales as volume. So it's clear that friction will somehow get much worse when the object gets smaller and smaller, simply because it should scale like the area to volume ratio. To maybe bring back this point to you, let's examine a simple problem that we can do kind of with a back of the envelope analysis. Let's imagine a tire rolling on a surface. Your car loses, let's say, maybe a millimeter of thread every 5,000 kilometers or so when you drive it. Right? So an atomic layer, let's say, is 2 angstrom. That means 1 millimeter of thread is about 5 million atomic layers per 5,000 kilometers. Let's estimate that the car tire has a circumference of 1 meter. So 5,000 kilometers is 5 million rotations of the tire, which means that a tire loses about 1 atomic layer per revolution. Okay, and this is only rolling friction. So this gives you the idea that on the nanoscale, friction is really bad, and even for nanomachines to lose just 1 atomic layer, would very soon the machine would no longer work. On the other hand, friction is still hard. For instance, Richard Feynman wrote, he has worked on a number of problems. He worked on to understand friction, and he actually failed. As far as I know, he has not published anything very substantial about it. So why then renewed interest in nanofrictions? Beside the problem being important for nanomachines, there's now this situation where computers are powerful enough to perform direct first principles molecular dynamic simulations with tens or hundreds or even thousands of particles on the surface layer. So people can calculate all the atoms in bonds in the surfaces and try to calculate friction from first principles, or at least simulate it. The other big breakthrough has been in atomic force microscopy, where people can pull atomic scale tips over a surface, and they can measure this kind of slips. They can measure the force as a function of position, and they can actually resolve the stick-slip motion of such a tip on the surface. These are coming from individual slips over individual atoms. This was first achieved in 2004, so in the early 2000s. So one can also now macroscopic or nanoscopically study friction. Compared to what we have, these experiments are a little bit at a disadvantage because you never quite know what the surface looks like. Is it really one atom touching a surface? Is it several atoms touching a surface? Is maybe some dirt stuck between the atomic force microscope and so on? So you still have to do sometimes quite some assumption or modeling to explain these results. So the way we would like to build nanofriction from the bottom up is this is how we think about friction. There's some kind of surface, some kind of substrate here with a periodic potential that in the real friction comes from just the periodic arrangement of the atoms as shown in blue. Then there's an object, here shown in yellow as a support. And then the most important is there's a surface layer of the object, some kind of chains of particles. These are compressible. They are connected by springs to each other. They can move a little bit. And they are also connected by effective springs to the support. So this is the problem that we want to study. How does this map onto an ion trap? Well, when we have an ion trap, this surface layer here of the object will be our ions. It will be a linear chain of ions in a Paul trap. This periodic substrate potential that in real friction comes from the atoms will be just an optical lattice. It will be the periodic potential of an optical lattice. And finally, this attachment of this chain to the bigger object, to the support, will be given by a Paul trap. Basically, a Paul trap will give us an overall parabolic potential for these atoms, which acts as a spring force to them. And this is basically what Erio Tosatti and Hartmut Heffner point out, that one can make this very nice mapping, and therefore, by studying the physics of how ion chains move in periodic potentials, study how friction works. The reason why you need to use ions rather than neutral atoms that we can for a much longer time place in optical lattices is that you need these effective long-range springs between the particles. So atoms typically have just contact interactions, maybe magnetic dipoles, somewhat long-range interactions, but here we have real Coulomb forces that you can linearize and treat as springs in this problem. The other maybe important ingredient is that Tobias Schetz and co-workers showed for the first time that ions can actually be controlled in optical potentials. As I have said, for neutral atoms, we know that for a long time. But for ions, usually for ions, the optical forces are much too weak. And we had shown in 2013 that if you place ions in an optical lattice and say you move a single ion back and forth by several lattice sites, then when the lattice is off, you get this periodic potential. This is how we move the ions. And when you turn the lines on and when you turn the optical lattice on and make it sufficiently strong, then the ion remains pinned by the optical lattice in spite of the pulling of it on it by displacing the Paul trap. So this is what our experiment looks like. We have a standing wave of light. We use resonator mirrors to make the light intensity stronger. We have a Paul trap, which is a microchip trap that we can use to displace ions back and forth along this optical lattice. And then we have an imaging system that allows us to resolve in real time where the ions are. And we can measure even the position of the ions relative to the optical lattice with a resolution of about 10 to 20 nanometers. So this is what the real system looks like. There's a microchip, optical resonator. The ions are about 140 micrometers from the surface inside this optical lattice trap. We can make rather long linear chains of ions. This is something like 20 ions. However, all experiments that I will show you were performed only with up to 6 ions. And the reason is that we like to control the length of the chain. We need to average over a long time. And when we have too many ions, then while we are doing the measurement, we lose one of the ions, and then we cannot use the results. But even with 6 ions, as I will show you, you can enter a many-body regime. This is our imaging of the ions. What we do in this optical lattice is a Raman sideband cooling technique. People have talked in the context of neutral atoms about this earlier today. Basically, when the ion is at a node of the optical potential, like here, this is a node, this is a node, this is a node, then the fluorescence of the ion is at a minimum. And as we move the ion in a steep trap across the antinode back to the node, the ion fluorescence increases. So this distance corresponds to 185 nanometers, lambda over 2 in our optical lattice. And basically, this fluorescence curve gives us a calibration of the position of the ion. We can also, with a slit, image the ion where it is, but we typically use this calibration to figure out, via the fluorescence seen from the ion, where the ion is relative to its potential minimum, and in particular, the moment when it slips from one minimum to the other minimum. And we can have chains of ions and do this for each ion separately. So let's examine something relatively simple, the dependence of the friction on the normal force. So this is the so-called Prandtl-Tomlinson model of friction, basically a single particle. This is a single particle model that is connected via a spring to the object. The object is moving, and it's moving across the periodic potential. And what you see here is here's the periodic potential plus the spring. The spring itself, of course, can be modeled as a parabolic potential itself. So this is the combined potential of the Paul trap, the parabolic potential of the Paul trap, plus the periodic potential of the optical lattice that the ion sees. And as you see, as this trap is displaced along the lattice, the ion stays trapped in a local minimum, and at some point it slips. And each time it slips, it releases this energy in terms of heat. And then it gets trapped in another local minimum, slips again, and so on. In real friction, this heat that is generated by this slip is taken away in the form of phonons. In our case, we are continuously laser cooling the ion, and so basically we're taking this energy that is released out in the form of photons. So, and as I showed you, we have sublattice resolution. How then do we measure friction? Well, as I showed you in this movie, we ramp the force linearly up and down versus time, which means we linearly displace the position of the ion trap, of the Paul trap, forward and back, and we monitor the ion fluorescence. And so going forward is shown in green, going backward is shown in red. And so what we see is, say the ion starts out on the green curve near a potential minimum. It gets pulled up the maximum. At some point it slips. This is where it slips across the potential maximum. It recools into the new minimum, and then it gets pulled over another potential maximum. So this, what you see, is the moment when the ion slips. And what we observe is when we do the same process backwards, we see the slip happening at a different time, equivalently at a different force. And the reason is simply this stick-slip behavior where the ion does not follow the global maximum, but it gets stuck in the local minimum here. Sorry, it doesn't follow the global minimum. It gets stuck in the local minimum here and slips at the moment when this minimum disappears. And so basically, by looking at the hysteresis between the green and the red curve, the distance between these two fluorescence maxima, the moments when the ion slips, we can determine, if you want, the maximum static friction force. It's twice the maximum static friction force because we're going forward and back. So this distance is a measure on how hard can we pull on an ion, just like in a static friction force on an object before the ion slips. So we can measure this. We can also, as I showed you before, measure the ion position, essentially value of the fluorescence, how much fluorescence we have, calibrated, gives us the position of the ion. So we can basically reconstruct diagrams like this, where we show along this axis the applied force, and on this axis the displacement from the potential minimum. And so when we go one way, we see that the ion is stuck in a local minimum. As we increase the force, at this point it slips. And then as we go backwards, the ion gets stuck in the other potential minimum, and at this point it slips back. So the area enclosed by this F delta X diagram is simply twice, again twice because we go forward and back, is simply twice the dissipated energy per stick slip. Okay, so now we can plot either the area or the maximum static friction force, in this case the maximum static friction force, as a function of the corrugation parameter. Corrugation parameter is simply given by the ratio of the lattice vibrational frequency locally without the trap relative to the trap vibrational frequency. The corrugation parameter is proportional to the depth of the periodic potential of the lattice along this axis. So think of this axis as the depth of the periodic potential. And it's also equivalent, if you want, in a macroscopic system to the normal load. So what you would expect from the macroscopic friction law is that the friction is proportional to the normal load, so you would expect a linear behavior like so. What you see, what we measure, and what also comes out directly from the Prandtl-Thompson model is an approximately linear behavior but with an offset. And the offset is rather easy to understand. This is what I've shown you before. When the lattice is deep, but not too deep, we have one extra minimum, and there's the stick-slip friction like so. However, if the lattice is too shallow, like in this situation, or the other external trap is stronger, then the lattice is not deep enough to create two minima. And in this case, even though the ion is moving in a periodic potential, basically there's only one minimum. The negative curvature of the lattice is not sufficient to overcome the positive curvature of the trap. And so in this case, you have only one minimum. You have no stick-slip friction, and therefore you have no static friction force. So basically here the lattice is deep, and then in units, in this dimensional corrugation parameter, stick-slip friction is supposed to set on at 1, like in this Prandtl-Thompson model, and this is indeed what we see. And this just tells you that in real experiments, you're always well above this critical corrugation parameter, and that's why you see this approximately linear dependence of the friction on the normal load or the depth of the potential. So now let's look at velocity. We said before, we teach our students that stick-slip friction of one hard surface on another, is independent of velocity. When we do the experiment, just like we did before, so we take curves like this, but now we measure the enclosed area or the static friction force, the distance between the hysteresis maxima. When we measure them versus velocity, and here we measure over almost 5 orders of magnitude of velocity. This is a logarithmic velocity axis. We actually see that the situation is not so simple. This is the friction force. We see a region when we move very, very slowly where the friction force is essentially 0. We see one region, one intermediate region of velocities where the friction force increases logarithmically with velocity like so. We see a region where the friction force is approximately independent of velocities. We have other plots where this region is wider for these parameters. This is a relatively narrow region by about a factor of 10 velocity. And then we see a maybe even more counterintuitive region where the friction force falls off with velocity. So you can kind of have all kinds of possible behaviors for the friction force as a function of velocity. Let's try to understand what is going on. It turns out that in this problem, we have 3 time scales. So we have a transport time scale, which is basically saying at a given velocity, how long does it take to move the ion trap by one lattice side? This is what we call distance, the period of the lattice side A divided by the velocity. So this is the transport time scale. That's one time scale that depends on velocity. And then we have 2 time scales that are independent of velocity. One is the thermal time scale. So the ions are at finite temperature. They are close to the quantum mechanical ground state, but not quite. They're at finite temperature. And so they have a chance of hopping between 2 minima. This is what I call the thermal time scale. Okay, so they can hop thermally over the barrier. And then it turns out that there's a 3rd time scale, which is the recooling time scale. So let's imagine that we transport very, very slowly. Then what's happening is that this transport time is much slower than the thermal hopping time. And basically, while we're very, very slowly displacing the minimum of the trap, the ion has time many times back and forth to travel over this potential maximum and reduce friction. And so let me show you maybe a movie for that. So what's happening here is you have, again, the same situation as before, a bistable situation, 2 minima, but now the ion is hopping back and forth many times so that it can at each time maintain the Boltzmann population that you expect for thermal equilibrium between these minima. And so you see, instead of the ion actually slipping over the minimum of the lattice, it just kind of thermally averages back and forth and follows the global minimum, and stick-slip friction disappears. So this is what people call thermal lubricity, reduction of friction by temperature. So that is this regime. Then there's a regime where friction depends logarithmically on velocity. This is basically the region where the thermal time scale and the transport time scale compete with each other. So they are comparable, and therefore the faster I transport, the more often I see stick-slip friction as compared to just thermal hopping. And so that leads to an increase of the friction force. In this region over here, our transport time is always much faster than the thermal hopping time, and so basically we see the maximum friction. You can think of this, the ion each time sticks and slips, as I've shown you in the original movie. And finally, over here, what happens is the ion, as it slips, needs some finite time to recool, but before it has time to recool, the lattice has moved to the next minimum. Okay? In that case, you can think of the ion as effectively being hotter than it was before, and therefore stick-slip friction happens less. And this is responsible for this counterintuitive reduction in the friction force. And this is what we see experimentally. For slow speed, we see a large hysteresis and the ion slipping. And then for faster motion or equivalently higher temperature, we see the situation where the friction force is reduced. And also the number of instances, these are average curve, the numbers of instances when the ion actually slips over the barrier is also reduced. And that's why this fluorescence is lower. Okay, so we understand, we think, for a single particle, dependence on the load, on the depth of the periodic potential, and the dependence on the velocity. Let's look now at the dependence of the friction on the surface. So in this case, we are no longer looking at a single particle problem. We look at a chain of particles connected with each other through springs, traveling in a periodic potential. So there are a few parameters of interest. One is the period of the lattice A, that I will call A. The other is obviously depth of the potential, periodic potential U. Then what is relevant is the springs between the particles and the springs with which the particles are connected to the moving potential. For us, these are related because they are both somehow scaling with the Paul trap, right? K is set by how tightly we make the Paul trap, and G depends on how many ions we pack into a given Paul trap, because that determines the spring forces between the particles. And finally, most interestingly, there's also a separate length scale D, which is the equilibrium distance of the ions when the periodic potential is not applied. And even though we don't have an equal spacing, you can think for the moment as a periodic spacing of the ions of some scale D. For us, this A length scale is about 180 nanometers, and this length scale D between the particles is anything between 5 microns and 15 microns or so. So D is much larger than A. Okay, and now what we can do is we can arrange it in such a way by slightly adjusting the Paul trap so that D, this length scale D, is a multiple integer of this length scale A. So that basically all ions are sitting at equivalent points in the periodic potential. So this is a measurement with with 3 particles, ion 1, ion 2, ion 3, that are arranged so that they sit at equivalent points in the periodic potential that we move then across the lattice. So here the force is going one way. At this point, ion 1 slips, ion 2 slips. They all slip together across the barrier. High count rate means this is the moment of a slip. Here's the moment of another slip. And then when we move the force in the other direction, we see this clear hysteresis, namely that there's a distance between this slip and that slip. And you can see also very easily that all the ions are doing essentially the same thing. They all slip at the same time. When we plot, for instance, the static friction force or look at the dissipation, it's simply n times, in this case, 3 times the single particle dissipation. Not too surprising. All the ions are doing the same thing. So in a movie, this is what it looks like. You know, the ions are matched to the periodic potential. They are connected with springs to each other. But you see, because all ions are equivalent, these springs between the ions never really matter. They never get stretched or compressed. And so what you see is just a single particle physics for each ion as it gets pulled over the lattice side and then recooled into the new minimum. That's why it's simply n times single atom stick-slip friction. It gets much more interesting if we arrange the ions in such a way that they're not sitting equivalent points in the periodic potentials. So if I plot the ions, say the phase of the equilibrium position of the ions versus the lattice, then what I have shown you before is the so-called match case, where all the ions are sitting at or near equivalent positions in the optical lattice potential originally. However, you can also arrange, by changing the ion spacing, a situation where, for instance, an arrangement like that, where the average force on the crystal, the average force on the center of mass vanishes here. I have arranged them in such a way that the average force vanishes. This ion sees one force, this ion sees the opposite force, etc. for 6 ions. So in this case, the physics is different. When we do that, here again shown for 3 ions, compared to the previous case, you can see that the dissipation is drastically reduced. So I should point out, compared to this case here, we have just very slightly, by a few 10 nanometers, changed the spacing between the ions on a distance scale of about 10 micrometers, and friction is drastically reduced. So you see there's almost no hysteresis left in this problem. The ions almost don't slip. And also what you can see is now, instead of the ions all slipping at the same time, whatever residual slipping remains, they do so in a staggered fashion. And there's also almost no hysteresis left. So ion 1 slips, 2, 3 slips. So this is what it looks like in a movie. So now, again, otherwise everything has been kept the same. The ions have been slightly rearranged relative to the optical lattice. And now you see what happens is, say, one ion goes over the barrier, it pulls over the next ion, pulls over the next ion, and so on. So it's a caterpillar-like motion. And one way to think about why friction is reduced is now you can see that the springs between the ions get periodically compressed and stretched. So the energy that was before kind of released as heat as the ion slips over the barrier is now stored reversibly in the springs between the ions, in the Coulomb forces between the ions, and released. And so this motion leads to much reduced friction. This effect was predicted in the 1980s for the first time, and at the time was named super lubricity. There's a little bit of an inflation of super, maybe, because the friction here is not really going to zero, it's just reduced. So maybe structural lubricity would be a more appropriate name for this effect, but we see it rather clearly. If we plot now the observed friction force as a function of this matching parameter, so this matching parameter is simply the averaging of the force. Matching parameter 1 means all the ions experience the same force. The center of mass, the force on the center of mass is maximum. Q equals 0 means, sorry, this should be mismatch Q equals 0. Q equals 0 means the force on the center of mass is 0. So when we vary this matching parameter continuously, we see that kind of 2 regimes. One is where the force drops as we change the matching parameter, and then it remains more or less almost constant. Here, the friction force is plotted also on a logarithmic scale. So maybe the biggest result of this experiment was that even for 2 ions, we see, just from the matching versus mismatching, a reduction of the force by a factor of almost 10. For 6 ions, we see a reduction of the friction force by almost a factor of 100. So when superlubricity was first predicted, always very long chains were analyzed. because they're easier to analyze, infinitely long chains, and it was somehow believed that this is a many atom effect that you need to have many atoms or ions to see this effect. But we see that a very drastic reduction is already observed for just a few ions, in this case up to 6 ions. The dashed lines are T equals 0 calculations if the atoms were at 0 temperature. And the solid lines are numerical simulations for our system. So you can see that about half on a logarithmic scale, about half the reduction comes from T equals 0 superlubricity, and the other half of the reduction comes from finite temperature. Let me explain to you why that is. So it turns out that when you plot for, say just a 2-particle example, if you plot the so-called Payas-Nabarro potential, the effective potential in a plane that shows the position of the first particle and the position of the second particle. Then if the particles are matched in their distances relative to the periodic potential, you have these 2 minima with a high barrier in between them. So the ions are cold. They're much colder than this barrier, and therefore you see essentially the full stick-slip friction as you move this barrier over. So the ion has to kind of hop over this barrier or is pulled over this barrier. When you rearrange these 2 ions in what you would call the superlubric or structural lubricity situation, it turns out that this barrier between the lattice sites is much reduced. So before we were at low but not 0 temperature, now our temperature may become comparable to the new barrier height. And therefore, we are now much more sensitive to temperature effects. So you can think of the structural lubricity as reducing the barrier in this Payas-Nabarro many-body potential between the minima, and therefore temperature now starts to play a role. And so basically what I'm showing you in this graph is that we would see, say, for 6 ions, a factor 10 reduction if our temperature was truly 0, but because we have a small finite temperature, but the potential gets reduced so much that another factor of 10 comes, if you want, just from structural thermal lubricity in the system. So maybe one way to think about it is the following. Imagine 2 particles, and they are connected with some solid bar between them. So, of course, if they are sitting at equivalent points in the potential, they experience the same force. And as I said, we argued before, this is just like single particle friction. If the particles are sitting at opposite forces and they're connected by a solid bar, then of course the force on the ions, the center of mass force is always 0, and you wouldn't expect any friction. Now, if you want, the surprising thing about superlubricity is that even if you connect the particles just by a string, not by a stiff bar, so that the particles can move in response to the force, the superlubricity, this reduction in the friction force, still persists. So basically, this near 0 friction persists for finite spring constant. Superlubricity has also been observed in real friction system. This is an atomic force measurement. So they basically used the graphite flake and moved it across the graphite surface, and they saw that the friction force depended on the orientation of the graphite flake relative to the graphite surface. And this was interpreted as superlubricity, that for certain angles, the distance between the particles does not match basically the period of the lattice of the surface, and therefore the friction changes. However, these results were not really reproducible, so sometimes they would measure this, and a little bit time later, they would just measure a very large friction force. And so it turns out that for these graphite flakes, for instance, there's also a torsional force that likes to align the friction. So to align the atoms in the object with the substrate, which makes this effect go away. Plus, it's not so clear, for instance, whether this is a 2-particle effect or a 10-particle effect. It's not known how big the graphite flake essentially is. Okay, now I would like to switch gears in the remaining few minutes. I would like to tell you about the relation between nanofriction that I've shown you before and if you want, the static, which is the dynamic phenomenon, and the static phenomenon, the so-called Aubry transition. So Aubry analyzed in the 1980s, he was a PhD student, and he analyzed a problem of an infinite chain connected by springs to each other with some characteristic period d, subject to a periodic potential with some characteristic period a. And he asked himself, there's no motion, these ions are arranged, it's an infinitely long chain. And he asked himself, if d and a are not commensurate, and you turn up the strength of the periodic potential, what happens to the chain? Naively, you would say at some point the spacing between the ions when the periodic potential is deep enough will no longer reflect the original distance scale d, but must somehow rather reflect the scale A of the periodic potential as the ions will be pulled to a minimum. However, what Aubry found surprisingly, as the periodic corrugation potential is increased, so you might have thought, well, let's look at this particle here. As I increase the strength of the potential, this is really a bistable or unstable point, and at some point the particle will like to localize either here or there. So you might have argued that, at some critical strength, maybe this particle gets localized. And then for some other particle at some other strength of the optic potential, this particle gets localized. You might have expected that particles kind of localize one at a time, naively. At least that's what I would have guessed. However, what Aubry found is that as you increase the strength of this periodic potential, there's a sudden moment where all the particles localized in the new periodic potential. So they all suddenly localize at some critical potential depth. So let me show you a small animation for 100 particles. So what I'm showing in this axis is the position of the particle modulo the lattice potential. So we have 100 atoms, and they are sitting on all kinds of possible positions relative to the lattice. This point labeled 0 is a potential maximum. These points labeled minus 0.5 and 0.5 are potential minima. So if the periodic potential is very weak, this is approximately a line where there are 100 particles in here, and they occupy all different positions of the particles, all different positions relative to the lattice. And here what I'm showing you in this axis, so this is the initial position relative to the lattice, is the final position relative to the lattice for a given potential strength. And so in this animation, the strength of the periodic potential is slowly increased. And so what you see is at a sudden point, this chain breaks apart. And we see a number of gaps. And it turns out, and this was the other very interesting fact about this kind of transition, is that this distribution is fractal. So no matter where you zoom in on this, you see more and more gaps. It's almost like a devil's staircase, not quite the same thing. But basically, this is a curve that in the infinite limits is nowhere differentiable. There are nowhere two particles that don't have a gap relative to the lattice. So basically, more and more gaps form, and they form all at the same time. So what is the physics behind this kind of maybe somewhat surprising mechanism? One way to think about it is the following. So let's think about the particle that was sitting near the maximum of a potential like before. As I increase the periodic potential depth, at some point this particle will go unstable because it will be favorable for it energetically to localize here or there rather than sit at the top of the periodic potential. So that particle, which is this particle over here, will not like to sit near the top of the periodic potential. It will have an excluded region for a given periodic potential strength. It will basically not like to sit at the top or near the top. So as this particle localizes either to the left or to the right, what it does via the spring forces, it pushes the next particle over. So basically, there's a primary gap that opens up for this particle sitting at the top of the periodic potential. As it localizes in its new minimum, it pushes the next particle over, and because this particle has a forbidden region of positions, the next particle will have also an albeit smaller forbidden region of positions. So there will be a secondary gap for the next particle, and so on. There will be a tertiary gap for the next particle. So basically, this perturbation of the particle that first went unstable propagates down the lattice, albeit exponentially weaker. So this is the physics. The chain basically breaks up into this fractal distribution. And the other thing that Aubry found is that if you ask yourself, what is the point at which how long can this chain resist the periodic potential before it breaks up in this way? He found that the longest, the highest critical potential was when this scale of d over a, the ratio of the two length scales modulo 1, basically the ratio of two length scales, equaled the golden ratio. In some sense, of all the possible irrational numbers, square root of 2, the golden ratio is the most irrational number. It's the worst that the mismatch can be, and therefore this chain resists the longest the action of the periodic potential. Okay, I showed you this with the primary and secondary gap. Now, how is this related to our physics? Well, these forbidden regions in the static problem are exactly the regions where, as we pull the lattice over in one direction, the particle jumps from one lattice side to the next, right? It jumps from the local minimum to the global minimum, right? Because it doesn't like to sit on this periodic potential. So basically, if you move this very, very slightly or very, very slowly, what you can see is this forbidden region corresponds exactly to the forbidden region of the Aubry transition over the gaps. The particle doesn't like to sit at the gaps. So to wrap up, when we measure this, we see a gap opening. Here we're changing the strength of the potential going downwards, and we see the gap opening up. And we see this is the primary gap for the first particle. This is the secondary gap, about 10 times smaller in width for the second particle, and so on. So we can measure this kind of dependence of friction force on the strength of the optical lattice for one particle. This is what I've shown you before, the Prandtl-Tomlinson model. And then we see that the superlubricity persists longer and longer the more ions, this is 2, 3, and 5 particles, the more ions we pack in the chain because the spring constant gets stronger. So maybe one story to take home. Phil Anderson said more is different. Something that we have also learned from our experiment and from Selim Jochim's experiment is that often more is not that many. So with 3 or 5 particles, you can see essentially the physics of very, very long chains. What's next? Maybe let me just show you one thing that we would like to try to do next. If you think of the ions now being truly in the ground state in a weaker potential where tunneling can happen, then like in a Mott-Hubbard model, the ion likes to delocalize, to decrease its kinetic energy by tunneling to the next neighboring lattice that will decrease its kinetic energy. On the other hand, there's a price to pay. As the ion tunnels, say, from here to there, it's closer to the next ion, further away from the ion on the left. To first order, there's no energy change, but to second order, there's an energy change. And it turns out that the Coulomb potential is so strong that this energy change can be quite comparable or typically even larger than the kinetic energy. However, for a typical distance of, say, 10 to 15 micrometers between the particles, these two length scales will be comparable. And now you can ask yourself, is the ground state of this system for a given distance between a particle or a given interaction strength, is it superlubric? Is it a delocalized state? Is it a superfluid state? Or is it a Mott insulator-like state where basically the interactions between the particles prevent the tunneling in this lattice? So it's a little bit reminiscent of the Hubbard model. However, these are long-range interactions, not contact interactions, that would prevent the tunneling of the particles. So maybe my time is up, so I would like to conclude here, and thank you for your attention.
So thanks so much for this glimpse at what atomic physics can tell us about friction. Are there questions? I think that's the first question over here.
This is absolutely beautiful. A question, the difference between static and dynamic friction.
So it's a very good question. So static friction is what we measure here. We are basically measuring as we displace the trap and pull harder and harder on the ion, which is linear in the displacement. When does the ion first slip? Kinetic friction is very, very complicated because kinetic friction often has a memory aspect to it, right? For instance, even static friction may have a memory aspect to it because for certain materials, the longer the particles sit on the surface, the larger the static friction force, for instance, becomes. I'm not really sure how to measure kinetic friction in our system. Maybe one slight inkling is when we move very fast compared to the recooling time scale, we see the friction go down, right? Kinetic friction is typically smaller than static friction. Our experiments, the interpretation is relatively simple. The ions don't recool fully to the new potential minimum, and therefore friction is reduced. You could imagine that something similar is happening in kinetic friction, where the ions or the particles just don't have time to really find the local minimum, maybe all the energy being taken away into phonons. But I'm really not sure whether the physics of kinetic friction is the same. And I'm not aware of any good model, for instance, that would distinguish kinetic friction from static friction, except these molecular dynamics numerical situations, which have to do with time. Do the particles have time to find the minimum energy rearrangement or not? But it's a really interesting question. Mm-hmm.
So there's another question back here.
There's one back, one here. Okay, go ahead.
So if you argue with number theory that this is the most rational number, Do you have any intuition for what the next most irrational number would do? And do you have an intuitive picture at all? It's like throwing this into the other potential and then having to find the potential with the most oscillations or something like that?
Okay, I have no idea what the next irrational number would be, but maybe I should. I can give you some intuition why the golden ratio is so good. So if you ask yourself, I have many particles distributed with random phases on a circle to minimize the friction force. So basically, the friction is certainly minimized when the force on the center of mass is minimum, right? Then how should I distribute particles on a circle like so that they experience the most unequal phases? Because that means the most opposite forces. So if you start with an ion with this phase, particle with this phase, if you place the next particle over here, that's great for two particles, but the third particle has a pretty similar phase. So it turns out the best way to maximize this distance between the particles is to place the first particle here, golden ratio, the second one there, the second one there. So the golden ratio is the arrangement that keeps the gaps the biggest in some average way, and that's why the golden ratio is there. What the next most favorable, I have to look at Aubry's. I don't know whether he solved the problem either. I'm not aware of it, but basically this is the physics of it. When we measure arrangements like this, we can do this kind of star-like arrangement, which is an approximation to the golden ratio, or we can make something where we average the force out, but the first particle is here, the second particle is there, and so on. We see a slight difference in the friction between these two scenarios, although both are kind of superlubric. Right? So the lowest order effect is simply make the friction force on the center of mass 0. And then the next order effect is make it as different as possible for different particles, and that's where the golden ratio comes in. Mm-hmm.
There's one more question back here.
One question. How goes the velocity dependence of friction when you have more ions in a mismatched case? Do you still see like this increase in friction with increase of velocity at one point?
Yes, you definitely do. Maybe I'll show you just 1 versus 2. I have a graph for that. Let's see. So basically what you see qualitatively is here's, for instance, a graph for the velocity of dependence of friction for one particle, which is roughly what I show, and two particles. So roughly those 4 regions exist. One way to think about it is because the barrier of the potential is reduced for more and more particles, the thermal regime kind of broadens. It's equivalent to doing experiments at a different temperature. Because what matters in the end for these kind of graphs is the ratio of the temperature to the Pias-Nabarro barrier over which the ions are pulled. So essentially, when you put more and more particles, it's like increasing the temperature for a single particle. But all 4 regimes are still visible. Thank you. Very good question.
So I think we should move on, but let's thank the speaker once again. So Jianwei Pan wasn't able to make it as